Last year, we won the Create Award in the Science Division at the VEX Robotics 2016 World Championship. Using the VEX Gyro and our odometry code, we were able to accurately calculate its position on the field and automatically aim the turret and shoot the balls into the net.
In doing this through testing and research, we learned a great deal about the VEX Gyro. We wanted to provide this information to the VEX community so everyone could understand how the gyros work, why and how we need to calibrate them, why gyros drift, and strategies to overcome the drift so everyone can accurately determine direction. The first thing we would like to show is what the gyro actually does. We have a gyro mounted here with its output, which is just a voltage, going through this oscilloscope. When it is not rotating, the gyro produces a steady reference voltage. While you are rotating the gyro counterclockwise, the voltage output increases proportional to how fast it is rotating. When the rotation stops, the output goes back to its reference value. While you rotate the gyro clockwise, the value decreases in the same way.
Robot C is doing a bunch of work behind the scenes for you to integrate all of those voltage changes in degrees per second to provide you with a simple final angle you can read. To show what the Cortex is actually seeing, and to show why the gyros must be given time to calibrate, we have moved the gyro output to a port configured as a potentiometer. This lets us see the raw A to D value when the gyro isn't rotating. Each gyro will produce a slightly different reference voltage. Robot C takes a little under 2 seconds to measure and calibrate itself to this static condition. It is absolutely critical that the gyro remain completely still during this time, or else the calibration will be wrong.
Also notice the way the A to D value bounces around by a small amount. The Robot C developers create a dead band around the calibration point so that noise doesn't cause their calculated angle to drift.
The 2-second settling time isn't a concern because this can be done in pre-autonomous. Our code to calibrate and scale the gyro output is shown here.
This is the test fixture we use to do all of our gyro testing. In the previous code example, the sensor scale gyro was set to 98. This is far too low and produces a measured angle of 126 degrees when the gyro is rotated through 90 degrees.
For this particular gyro, the correct sensor scale gyro value is 136. This produces the correct angle. You will need to test and find out what sensor scale gyro value works for you. The gyro will never drift if it is still. For this gyro, 100% of the drift is due to vibration. This is a simple electric toothbrush. You can see what happens to the angle when we vibrate this test fixture. The amount and direction of drift is dependent on the frequency and amplitude of vibration.
You must do everything mechanically possible to prevent vibration from your robot's movement to get through to the gyro.